In this lesson, we will be using substitution, or the substitution method, to solve linear systems. We've used graphing before, and we've talked about the point of intersection being the solution to the system, as well as being the break-even point. But now we will be using substitution specifically. And then there are a couple of other ways too, specifically elimination or combination. There are a couple of names for it. But first of all, we need to remember what the standard form of a linear equation is. If you'll recall, it is ax plus by equals c, and where a, b, and c are constants. They're numbers. And we like them to be integers. Now, they can be decimals, especially where we are talking about money. But we do like them to be integers if they're not specifically a good reason to be decimals or fractions. The substitution method specifically is where you have, of course, a system of equations. So you'll have two equations. And so one of the equations, you must isolate either x or y, and then substitute the expression that that variable equals into the other equation. And so you end up with one variable, and you solve that equation for the variable that you have, and then you have to plug it back in. Sounds very complicated, but I'll take you through the process. It's not that complicated. So let's start with an easy one. So you can see the system that we have. They use that set brace, as we know it, to indicate that those equations go together. Now, if we were going to just think about how it looks, x equals -3 would be when we go back 1, 2, 3, and there's that line. And then y equals 2x plus 5, going up 1, 2, 3, 4, 5 is where it would start. And from there, you'd go up 2 and right 1, or down 2 and left 1, down 2 and left 1. And so you'd get this line. So we know that the point of intersection is somewhere around here. So that would be by graphing, but we want to do by substitution. So we take the value where x equals -3, and we replace the x in the other equation. So y equals 2 times -3 plus 5. And so the y value is going to be -6 plus 5. So the y value is -1. And our solution is the ordered pair. We already know the x coordinate, -3, -1. And isn't that what we saw just a moment ago? That's about where that point of intersection looked like it was, left 3 and down 1. So now we'll try one where we have, it stepped up a notch. Again, we could graph these and get an idea of where they're going to end up. I just want to jump right into it. Now, notice that we know what y equals in both situations. Y equals -x plus 2 in the first equation. Y equals 3x plus 10 in the second one. And since we want the y value where they're equal, we can simply replace this y with this expression. Since the y's are equal, I can put -x plus 2 in place of this y. So that's what I'm going to do. And I write it out. -x plus 2 equals 3x plus 10. And now I solve for x, and I will find half of my solution because I need an x and a y coordinate. And I like to take my variables to the left, so I'm going to start by subtracting 3x from both sides. And that gets rid of the x's, and I get -4x. And then I'm going to undo the plus 2 by subtracting 2 from both sides, which gets rid of the 2 on the left side. And that equals 8. And now I divide both sides by -4. And x equals -4, -2. So now I know the x coordinate, -2. Now I don't know the y coordinate yet, but it should be quickly attainable by replacing the x in either one. In fact, both. That's a great way to check. So the top one, y equals -2, or another way of saying it is the opposite of -2 plus 2. Well, that makes it a positive 2 plus 2 is 4. So I believe my y value is 4. I'm going to check it by plugging it into the other equation as well. y equals 3 times negative 2 plus 10. And of course, 3 times negative 2 is negative 6, and negative 6 plus 10 equals 4. So I'm confident that my solution is negative 2, 4, and I should always be boxing my solution, right? So this is the ordered pair. These are the ordered pairs where those systems of equations or those lines cross each other. So now we're increasing the difficulty level just a little bit more. You see that we have another system of equations. This time both equations are in standard form. And we need to isolate. If we're going to solve this by substitution, we have to isolate one of the variables. Now, hopefully you can see which one it would be most advantageous to isolate. We've got a 1x, a 3y, 5x, and a negative 2y. Well, the strategy is always to isolate the variable that has a coefficient of 1 or negative 1 if that's possible, because then you don't have to divide by anything. If I was going to isolate the y here, I would have to subtract the x from both sides and get 7 minus x and then divide everyone by 3. Then I'd be dealing with y equals 7/3 minus 1/3 x. Or either one of these two, I would end up, if I've isolated y, everything would be a half, like 5 halves and 1 half. Or if I isolated x here, I would end up with a positive 2y on the other side, but it would be 2/5 and 1/5. So you always want to isolate whichever variable has a coefficient of 1 if it is at all possible. So I'm going to take the top one and subtract 3y from both sides. So x will equal negative 3y plus 7, or you can write it as 7 minus 3y. Either way is fine. And I'm going to replace the x in the second equation. Now this actually tends to be a difficult thing for students to do. A lot of times I see students wanting to put this expression in place of the y, because they see the y here and they want to put it in the y here. But remember, x equals negative 3y plus 7. So we want to replace the x in the other equation with the expression that x equals. So that's what we're going to do. So 5 times x, and x now is negative 3y plus 7 minus 2y equals 1. So now I need to distribute. 5 times negative 3y is negative 15y. And 5 times a plus 7 is plus 35. And I write down everything else. Minus 2y equals 1. Well, I see that I can combine like terms on the left side, and I need to get rid of the 35, and I need to combine it with its like term on the other side. And the way that we have to change sides of an equation is by inverse operation. So I'm going to subtract 35 from both sides. It gets rid of it on the left, and I'm left with negative 15y minus 2y, which is a negative 17y. And that will equal negative 34. Aren't we glad to see a multiple of 17y? So now I divide both sides by negative 17. And y equals, I'll have to write it off here to the side, 2. Now, again, I've found half of the solution. I've found the y coordinate. Now I can find the x coordinate by either plugging it into this y or this y, probably both, so I can check my work. What we really want to do is plug it in right here because x is already isolated. So maybe I should change colors here. So really what I'm doing is the x should equal negative 3 times 2 plus 7. Well, we know that that is negative 6 plus 7, which is 1. X equals 1. So the solution to this system is 1, 2. One way to check that now is to go back and check it in this equation that I didn't use to find the value. So does 5 times 1 minus 2 times 2 equal 1? And yes, 5 times 1 is 5, 2 times 2 is 4, and 5 minus 4 equals 1. So I just checked the x and y coordinate, and in both equations, essentially, and I again can put it right up here, 1 plus 3 times 2, and 3 times 2 is 6. 1 plus 6 is 7. So that solution works in both equations. So let's do a word problem. I'm going to need a little more room, so I'm going to move it off to the corner like this. So let's say Chad is having a pizza party. Gio's Pizza sells medium cheese, pepperoni, and sausage pizzas for $5.50 each, and 2-liter sodas for $1.50 each. Chad decides to get 1 2-liter for every 2 pizzas. He has $50 he can spend on his party. How many pizzas and sodas can he buy? So first we're going to write a system of equations. So the first equation that I see is this $5.50 for each pizza and $1.50 for each soda. And when you add up all the money, it's got to equal $50. So $5.50, and I'm going to use P for pizza, plus $1.50, I'm going to use S for soda, and that's got to add up to $50. Now the other one that we have, if we're going to do that fun little bracket, is this one right here. He decides to get 1 2-liter for every 2 pizzas. Now this can be confusing, and I see students mess this up every time. So if you're not sure, write them both out. Does the number of pizzas equal 2 times the sodas, or do the number of sodas equal 2 times the pizzas? Well, if we look right here, 1 2-liter for every 2 pizzas, he's going to end up with more pizzas. So I need to multiply the number of sodas by 2. And therefore I know that not the S equals 2P, but the number of pizzas equals double the number of sodas. So now I can substitute it in. This expression gets plugged in place of the P in the first equation. So then I have 550 times 2S plus 150S equals $50. So doubling 550, that's 11S plus 150S equals 50. So that's 1250 S equals 50. And then to solve for S, I divide both sides by 1250. And S equals 4. Now remember, I found it that it's 4 sodas. Very seldom do we write this one as an ordered pair. This time we usually just say how many sodas and how many pizzas he can buy. So now I'm going to replace the S, now that I know that its value is 4, in that second equation. So P equals 2 times 4, and that equals 8 pizzas. So for $50, as long as there's no tax, and of course that usually does come into play, he can buy 8 pizzas and 4 sodas. Now to check this, we do want to plug in both numbers. So 550 times 8, and that is 44, plus 150 times 4, which is 6, and 44 plus 6 equals 50.